Hello and welcome back to Calculus 2 section 7.2 on exponential models, meaning word problems where you get to come up with exponential model and work with that. Now, yes, you did have this in your pre-calculus course where you learned exponential functions, but now on top of that, we are going to add an extra layer where you guys are going to take either limit, derivative, or integral, or maybe all of them, right? To consider, you calculate something, right? So let's first remember that exponential model was y equals a e to the kt. And if k was positive, we call that growth, exponential growth. The y-intercept is the a, and the x-axis is t, time in which the y grows. If k is negative, then we are looking at decay, garbage decay, radioactive decay, carbon decay for carbon dating, right? And in time, that one decays. You know what else? Drugs metabolizing in a body, or killing off a virus, right? Where the top one is infecting with the virus. Do you understand that if one person that is sick gets in a contact with 10 people, those 10 are sick? Well, not all 10, but let's say 8 or 9 out of 10 are sick. And then they're going to go out, and each one of them, 8 or 9 people are sick. That's called exponential growth. It's not one infects one, and that one infects the one. That would be linear growth, right? But when one infects multiple, and each one of those infects multiple, that's called exponential growth. It's very easy to spread computer virus, to spread human virus, to spread the gossip, same thing, right? So anything that has that kind of network with a huge growth, right, it goes that way. Now, decay is, as you can see, much slower. Takes time for garbage to decompose, right? Less for organics, right? And our plastic bags, 10, 20,000 years. Again, not a problem for the planet. It's been around for 5 billion years already. So 10,000 years per bag is nothing. You're not saving planet, you're saving yourself, all right? It's like, I hate when they say, oh, save the planet, don't use the bag. Really? The bag is going to be gone in 20,000 years. This is nothing for the planet that's been around for 5 billion years and it's going to be here for 5 billion years to go, at least, right? So don't worry about it. Anyway, so this is our basics. And now we use this dressed up with different letters for different application. If I want to use the growth of population, I will say population in time is equal to initial population times e to the kt. And then this k is a constant of population growth. It has the birth and the death and a ratio of male, female. All of that stuff is in that k, mushed together, right? So that's what the k does. You can also go and say that the mass of an object is initial mass e to the negative kt, because now this is decaying. Could be a pile of garbage, could be a radioactive something, right? And again, that will be a decay. It's always the same model. It's just what is k, positive or negative, and we can associate that to our application. Now, population growth is something that we observe. Generally, I use census.gov. I just Google population clock, and population clock. Population clock, it's a .gov, so that's official for US, right? You see the population on the left for United States, 330 million. And you see the world population, still going up, okay. The world population of 7.63 billion, right? You also see the 10 top most populous countries where the Mexico overtook Japan 2 years ago. Japan used to be the 10th spot, and then Mexico passed. You have China, India. United States is third largest population in the world, right? China, you see it's almost 4.5 times larger in terms of population, right?
That might slow down a little bit now.
Evil. So, Brazil, Nigeria, Bangladesh, right? Maybe some of the countries you would not. I mean, Brazil is huge, right? And no, they do not count snakes. All right, cool. So what I want to do is I want to use this to develop the population model and then just think a little bit about it and then we go home. Sounds good? So we are going to pick up today's data as 7.63 billion. Cool? So when I jump here and I say population, I'm going to say in 2020, I have 7.63 billion. Now, I need one more data point before 2020. So pick a year that it's not immediately next to it, but pick any because we're going to ask Google to give us 2000. Because you like the round now, right? So we're going to go ask Google for 2000.
It says on the bottom that you could just ask the website.
Where?
Yeah. So
The United States population on February 10th, 2020. Select the date.
No, I don't want the United States. I want the world.
Oh, okay.
Yeah. World population 2000. Boom. 6.12 billion. 6.12 billion. Do we want to know anything specific in the future? What is the population in 2040? What is the population in 2060? What is the 2100? That's going to be a really bad number. But just because you asked, my friend, 2100 using this population model. Here we go. Our population model, which is the formula we memorized all the way back in our pre-calculus life, is this one. Now, we do not want to shovel 2000s. So we scale it down and we make this one to be our t equals 0, which means this becomes 0.6.12 as a data point. As soon as you have a point that has t equals 0, the other variable is immediately p0 or m0 or whatever the initial case is. So this immediately becomes p0. So we picked t to be 0 for the lowest year that we have, and technically we start counting time and nothing before that exists or we care about, right? So the new Big Bang 2000, right? The millennium bug, right? Since you picked that year. So now we have our model P equals 6.12 e to the kt. So we are already closer to our model. I need k. Yes?
So would you do P is the population in 2020 and T is 20?
Excellent. Yes. We are going to use 2020 7.63, exactly as you said, 20, 7.63. We have our time t, we have our population p, plug those in, and you will be able to calculate k. So 763 is equal to 612 e to the 20k, right? Because t equals 20 and k is what we are looking for. All right, it's time to divide 7.63 by 2.1. Now you use your calculators. You can turn your cell phone sideways to open the exponential and logarithmic stuff. They even programmed it for iPhones, so apparently it wasn't difficult enough. Use the real phone then. Yeah. So 1.2467, I'll leave 4 decimals because I can, is equal to, leave some space, e to the 20k, and I am leaving some space because I need to stick in now ln to kill that e. So now I'm going to push ln and then second answer to bring in the previous number so I don't have to retype it. And I will get 0.2205. 4 non-zero decimals. Always, please. 4 non-zero decimals. Equal to 20k. And finally, k is equal to, divide by 20, 0.04 non-zero decimals. So 1103. Finally, I have my model. Population in time is equal to initial population 612 e to the 0.01103 t. This is my population model if I use the numbers from 2020 and 2000. Now, Rory wants to know what is the year, or what is the population in year 2100. So, in 2100, we have t equals 100. So I have to calculate p of 100, which is 6.12 e to the 0.01103 times 100. So population in is what? 18 point? Well, just need the 1 decimal, and then this next one is a 4. We cut it off because our all others. Oh no, we had 2 decimals before, right? So 4, 4, and then what's next? 1, 4, 4. Okay, good. Billion. Oh, it's so not gonna happen. Why? Scientists believe that the carrying capacity of the planet is anywhere from 10 to 15.2 billion. That's the most generous one I've seen. Carrying capacity is a concept, you will learn more in differential equations. Carrying capacity is a concept which states that you cannot have larger population than that number because the planet has a finite surface area, finite resources, finite amount of farmable land, and it cannot support more than, and then insert the number once they agree, which is between 10 and 15.2 billion. And what we also know, the extra planets are not going to help because it's exponential growth. So we just have to figure out. Now, this was just the calculation. Let's do some calculus, because we haven't done calculus yet. All of this is what you were doing in chapter 3 all the way in pre-calc 1. Now, I want to take a look at this model and see if this model is a good model for a long-term prediction of the population. Now, to see if any mathematical model, and you get them in differential equations, is good, you send the limit to infinity, and then you analyze that. So, calc, fixed. So calc question on limits. We take our model, limit as time goes to infinity of our population, which is limit time goes to infinity of 6.12 e to the 0.0103 t. Now you know that the exponential model looks like this, so infinity. This is how we know that the model is garbage on the long run, because there's no way to have infinitely many people on the finite sized planet. You can't even have infinitely many bacteria or amoeba, right? Nothing. Nothing is going to be infinitely many. Yes, we do have 50,000 different species of spiders. Yes. But it's still 50,000. Nothing close to an infinity, all right? 50,000 is nothing. So when you look at this model, by looking at this model, you know that it's not good for the long run. But it's good for a short bursts, right? You know, let it work out 100 years in advance, and you can rewind it 100 years back. It should be okay, right? Should be okay. Now, what you can do is you can go and stick negative 30 in there and see if it predicts the population of 1970, right? Because you can Google the population of 1970. That's a record that you can find, right? So how well does this model hold against the previous population counts, right? You can check, and you will see that it starts deviating, right? You also need to understand that we doubled the population on the planet in the last 50 years. Can you imagine that 50 years ago, there was half of what we have today? Yeah, that's how quickly we are getting. And also realize that back in 1600s with the Black Plague, right? The Black Plague eliminated, killed 2/3 of the human population on the planet. 2/3. You know what that means? 2 out of 3 people in every group of 3 in this classroom is gone, right? So what is the better population model? It's a logistic model which involves what we call carrying capacity. Now, you study that in detail in differential equation, which is actually what I did this week in a population model, so you can at least see it. And there it is. Population in time is the carrying capacity of the planet times the initial population at the time you started looking. Initial population, carrying capacity, initial population, right? So you know all the numbers now, variables. That particular graph has exactly what you were expecting it to have, right? With the initial population, it flattens out at the carrying capacity M. And if you are to take the limit of that one, which is here it is, me doing that in differential equation class, you see that when you take the limit as time goes to infinity, your population is your carrying capacity of 150, right? So you will learn better models. Now, this is also not just for population. Again, diseases and viruses never kill the entire population. Black plague killed 2/3 of the population on Earth. Well, that means that a third of this classroom is still okay. You have to understand that humans are so different from one another that what kills one doesn't make a dent on the other one at all. You have people walking around with AIDS, they don't even know they have it. They don't even sneeze off of it. They transfer it to someone else, that person dies like that, right? So, even with the virus going on around now, no way everyone dies. Well, what's your lottery number, right? Yeah. There's that part. Sure, I understand. You should be freaked out, right? But it is not going to end us. Now, over there in differential equations, we also learn about the extinction, and we figure out how that happens, right? Why 90% of the species that ever exist are extinct, and so on, right? Sure, we can talk about that because that also has its mathematical place. So, much better model is the logistics model, and the logistics model is going to have that carrying capacity limit, right? And that's it. Since I have a -1 minute, I'm going to also mention that we can calculate the change in population in any year that you want. That will give you how many people were introduced to the planet in that 1 year. Now, that's going to be births minus deaths because everything is mushed together in that K. So, clearly, there will be way more births than what we see because there were deaths, right? So those cancel out, and then it's just the difference. So, to find the change in population, what do you have to do? Well, word change. Derivative. So, change in population is given by P of t prime. So if your P of t was 6.12 e to the 0.01103 t, your P prime of t is 6.12 times 0.01103 e to the 0.01103 t. You multiply these two numbers on the abacus. It's like $20 of gas right there. Times 0.01103, and we get 0.0675 e to the 0.01103 t. First of all, this is year 0, 2020, right? How many more new people we are going to introduce to the planet in 2020? Well, you stick in t equals 0. That makes e to the 0 is 1. So you are introducing 0.67 billion. That is 67.5 million people planet-wise. But that's a difference between the birth and the death, right? So way more babies than 67, because every baby that is born will cancel one of the deaths. And then when that's all canceled, this is the excess, right, of the 67 million added. You want to know how many you added last year? Put a -1. How many we're going to add next year? Put +1, right? So you can calculate the change in population 1 year at a time, because that's what derivatives do. And you can also take the integral from 1 to 3, and that will give you the accumulation, the total amount of people that are added towards the 3 years, right? If you go, I don't know, or 4 years or 5 years, whatever you pick. So we'll talk more about this next, I was about to say next semester. Next class, we'll finish this and then do 7-3. Be gone.